Numerical Computation, Chapter 5, Video number 5. We now derive a practical error estimate for the fixed point iteration. Assume that the fixed point iteration converges such that on the interval r minus a r plus a of our theorem, we have the derivative of our function g is less than m is strictly less than 1, and in absolute value. So from the error analysis, we know that e of k plus 1 is less than or equal to m times ek. So a simple induction argument shows that now e1 will be less than m times e0, and e2 will be less than m times e1, which is m squared times e0. So each iteration, your error is multiplied by a factor m. So iteration number k, the error there will be less than m to the k times e1. So this formula shows us how the error at a later time depends on the initial error and how fast it goes down to 0. But we would say that the result is still useless unless we find a way to estimate the E0, because everything depends on E0. So let's see how we can do that. So E0 is the error at your initial guess x0. So it's r minus x0 in absolute value. Now we play a little trick. It's a very standard trick. So we add a value 0 in here, and the 0 is written as negative x1 plus x1. And then we group the first two and the last two, and by triangle inequality, this will less than or equal to the absolute value of each and sum up. And we also notice that this one here, the first one, is exactly E1. Okay, so it's less than E1 plus x1 minus x0 in absolute value. And then we use our estimate. E1 we know is bounded by m times E0. Okay, so now we see we have an inequality involves E0 and other quantities that we actually can compute. So this will give us a way of finding E0. Okay, so indeed, if we move this term to the left and solve this inequality, we have the following. E0 is less than x1 minus x0 in absolute value divided by 1 over m. So pay attention. So this quantity here on the right-hand side can be computed, and we can know how big it is, and it gives us a bound on E0. So putting everything back together into this estimate here, we have ek less than mk over 1 minus m times absolute value of x1 minus x0. Okay, let's see how we can use this information. Okay, so here the first one is the estimate we derived on the previous page. And let's say there is a error tolerance epsilon, and we want to understand how many iterations are needed to guarantee the tolerance is satisfied. So therefore, at iteration ek, if we want the ek to be less than epsilon, we end up with this inequality. We see that here everything is given and k is my unknown. I can solve it with respect to k. Okay, by moving everything else to the right hand side and leaving m to the power k alone on the left hand side, we get this expression. And next we take a natural log on both sides, and we will have k times natural log of m, and less than the natural log of the whole thing here. And because m is less than 1, so if I divide both sides by ln of m, which is a negative number, I have to switch the inequality sign. So here's the solution for the inequality. K has to be bigger than this expression. So if you take the integer part of this number and the bigger integer part, and that gives you the minimum number of iterations needed to achieve a certain error tolerance. No, sorry, it's not max. This shall be the minimum number. Okay, let's take an example. Say we want to solve cosine x minus x equal to 0 with a fixed point iteration that we have done. And we have our initial guess, which is 1. And I want the error tolerance to be 10 to the negative 5. And can we find the minimum number of iterations needed? So we know the root r lies on the interval between 0 and 1. And we see that also all the iterations happen between the value x equal to 0 and x equal to 1.